And okay, so today we have Jiatu coming from MIT. He's a first-year PhD, and he's going to talk about his work. Can we find an empty pigeonhole efficiently?
Yeah, thanks for the introduction. And yeah, I'm Jiatu from MIT, and I'm a first-year PhD student. And this is a work I did last year with Rahul, Ilango and Range Avoidance on finding empty pigeonholes. So let's define the problem and see what does it mean by finding an empty pigeonhole. Okay, so let's start with some typical opening where we consider circuit complexity. And starting from like 1950s, we have known by Shannon that if you count the number of truth tables and you also count the number of small size circuits, you will know that most functions are extremely hard, which means that they require like exponential circuit size. So however, when people propose the research to actually finding one of the circuits that requires large circuit, it's somehow stuck. So we spent like 30, 40 years working on expel one of these hard functions, but we cannot actually find one. For example, you cannot find a function in non-deterministic exponential time that requires superlinear size circuit. So there is a sharp contrast to the fact that most of the circuits are equal. Most of the truth tables are hard. And also, this is not the only example of the hardness, because, for example, we know that a random truth table has large circuit complexity. We know that a random binary linear code has very good distance. And we know that a random graph has neither large clicks, has either large clicks or large independent set. It should be either one. I just noticed. And we know that random matrix is far from being low rank. This is called like Ramsey graph and gradient matrix. But apparently all these constructions are quite hard. We don't know how to do them in like polynomial time. So it's like so this kind of explicit construction problem is like you have a C where water is everywhere, but you cannot find any water deterministically. If you want to guarantee that I find some water, you cannot do that. And there is a quote from the Aurora Barrett book that it is quite surprising that explicit constructions are so hard, because a proof of existence via the counting argument or probabilistic method actually shows that most of the objects are good, but it's just hard to find the good one. So let's introduce this like empty pigeonhole principle, or sometimes we call it dual pigeonhole principle, where you have n pigeons flies into m holes where n is smaller than m, and there must be an empty pigeonhole. So this is some elementary school mathematics. And we want to say that actually all the examples above can actually be represented by this empty pigeonhole principle. And for example, we know the circuit lower bound case. What we are doing is that we first count the number of pigeons that are like truth tables. There are like 2 to the n truth tables of n-bit input. And we can always count the number of small circuits, where if you consider the circuit of size S, you can somehow enumerate all the ways to construct a SI circuit, which is like 2 to the O S log S. And if your S is like sub-exponential, then the number of holes will be extremely small compared with the number of pigeons. So there must be a pigeon, namely a truth table that is hard. And it's similar for the Ramsey graph, where there are like 2 to the n truth 2 graphs. But if you somehow count the number of non-Ramsey graphs, which means either it has a large click or independent set, then you can plant it's like if you count the number of graphs that has large clicks and independent sets, you can see that the number is extremely small if you set k to be like 0.1 times log n. So this shows that a random graph must either have large clicks or a large independent set. And also, if you count the number of matrices, say in Boolean matrices, the number of Boolean matrices is like 2 to the n squared. But if you consider non-rigid matrix that is close to a low-rank matrix, you can count by this kind of decomposition, because the low-rank matrix must be represented by two like rectangle matrix multiplication plus a sparse arrow. And if you count the number of ways to doing this, you can see that it is extremely small if you set the arrow to be small. So all these three problems can be reduced to this empty pigeonhole principle. And actually, people can actually define a computational task that capture all of this. So range avoidance is the following problem where you are given a circuit with n bit input to n bit output with m larger than n, and the output is to find a string that is not in the range of the circuit, which means for all input x, cx is not equal to the y you find. So this can be considered as like 2 to the n pigeons flies into 2 to the m holes, because this circuit just means which pigeon goes into which holes. And you must have a hole that has no pigeons flying into. And actually, this is also an example of explicit construction, because not only one, but many of the strings. For example, if you set m to be like n plus 1, then at least half of the strings should be a correct answer. So for example, if you take the circuit C to be like square, computing the square of a number encoded in binary, then the output should be a square-free number. So this is just a simple example of this problem. Does this make sense? This problem.
Question. If you solve this problem, do you solve the question about like how to construct a hard circuit?
Yes, so we can see. So actually, this is a very recent result of Gordon, although it's not very hard. It's like the following explicit construction problems can be reduced to avoid in deterministic polynomial time. For example, it's like finding a hard truth table of length 2 to the n against like 2 to the epsilon size circuits can be reduced to range avoidance, and also construct remedy graph, construct n-binary rigid matrix. All of them can be reduced to range avoidance. And in particular, if you solve the first finding hard truth table problem, you can also prove some circuit lower bound, like exponential time requires 2 to the epsilon n size circuit, because you can first find this truth table and then simulate it to construct the algorithm in exponential time that requires large circuits. So this,
Yes.
okay, cool. So all these proofs can be done in one sentence. That is, you consider the existing proof of this explicit construction problem, and you suddenly realize that this is just some empty pigeonhole principle, and you can use this range avoidance problem to simulate the empty pigeonhole principle to find this good instance. So although it may take some time to go through all of this, but it's a one sentence proof actually. So there are some like trivial algorithm to range avoidance where, for example, the first trivial algorithm is just output a random number, random string. So if you define the class FBPP to the functional version of BPP, then I say avoid is in FBPP. This is just a trivial one. You just output a random string. And another random algorithm is like, if you have an NP oracle, then you can first randomly find a string and then check whether it is an output by the NP oracle. And in doing this, you can make it a zero error algorithm, because you can repeatedly check this until you find the actual final string that is outside of the range. And so this is like FDPP to the NP, which means zero error algorithms. And these are like trivial algorithms. And actually, there are some like non-trivial algorithms. For example, the algorithm presented in Cotton, that if e to the NP requires circuits of size 2 to the 0.1 n, if and only if range avoidance can be solved in NP to the FP to the NP. So this is a very strong result saying that circuit lower bound with an NP oracle is equivalent to range avoidance with FP to the NP algorithms.
I'm sorry, what is E to the NP?
Oh, e to the NP just means 2 to the ON time with an NP oracle. E just means 2 to the NP, ON time. Okay. So here is some map which says that, for example, this means if you believe this circuit lower bound or you can prove it, then you can automatically get FP algorithm to range avoidance. Then you simultaneously get all these FP to the NP algorithms to this fancy problem, which we probably don't know. I think for these three examples, like Ramsey graph, rigid matrix, and strongly explicit two-source extractors, they are like with certain parameters, they are still unknown in FP2MP. So this can be considered as a systematic approach to solve explicit construction problems, because you do not need to take a look at each of them and just solve range avoidance, and you automatically got all the solutions. So this is quite an amazing approach to explicit construction problems. So here is this. We have, assuming circular lower bound, we have a P to the NP algorithm for a void. So there is a very natural problem within this table. It's like, can we solve range avoidance in polynomial time without NP algorithm?
Is that FP to the NP?
Oh yeah, this should be FP.
Okay.
Yeah, so the question is whether we can solve it in polynomial time. So I think if you haven't seen the paper, so you can make a guess whether the answer is opposite or like a positive or negative. You can make a guess.
Sorry, what's the bottom right part of the slide indicated?
The bottom, which line?
The bottom right, like what is it? The part about avoid NP to NP.
Oh, this means there is a derandomization algorithm of the trivial DTP to the NP algorithm, which runs in polynomial time with the NP oracle. This is kind of a derandomization version of the algorithm above. So our question is whether you can also derandomize the trivial algorithm that simply generates a random string and obtain a deterministic polynomial time. Okay. So how many people guess the answer is yes, we have an algorithm?
I still have a question about the bottom right. This is like assuming.
Oh.
Because like on the previous slide, I thought you were like, oh, the best algorithm you know is.
Yeah.
We don't know if it's.
Yeah, we all need to rely on this exponential time circular lower bound.
Okay.
So the question is not about how to prove it. The question is about the ground truth. So it's like, are you willing to believe that range avoidance in FP, or are you willing to believe that it's not?
Sorry, another question. So this de-randomization is it explicit? Or like this assumption like just gives you some circuit that is a sub-exponential, right?
Oh yeah.
But you don't know what circuit it is.
Oh, I see. So actually this is actually a reduction. It's like if you have a language of this, I can construct an algorithm using this language. If you give me this language and this algorithm, I can spell out the algorithm.
I see.
So this is kind of a reduction.
Yeah.
Okay.
I guess it should be in FP.
Should be in FP. Should not. Okay, should not. Okay. Yeah. So actually there are like because if you got a deterministic algorithm for range avoidance, you will almost get everything in explicit construction. For example, if you have the deterministic algorithm for a void, you will also get like circular lower bound. It's like there's no NP. Sorry for that. It's like if exponential time requires maximum circuit complexity, and you also get polynomial time algorithm for Ramsey graph, polynomial time for two sources extractors, and polynomial time for rigid matrix. You get everything. So a natural idea is that considering that all these problems are so hard, so maybe it's too good to be true, because if it's in polynomial time, then all of the problem automatically solved. But there is also another argument which says that after all, we believe all this consequence to hold, right? We do believe circular lower bound. We do believe explicit construction in rigid matrix, and we do believe we can construct some good like two-source extractors. So considering all these consequences are like in our belief, so why don't we believe this algorithm is easy? So there is like a controversy between this kind of problem. So actually there is a quote from Ren, Wang, and Sensing's paper. It's that we don't know whether a void is in polynomial in FNP, which stands for non-deterministic polynomial time algorithm. It's like non-deterministic search algorithm, or it's in polynomial time algorithm, or the negations are implied by any possible assumptions. And as far as they know, they do not even have a good idea about what the ground truth should be, because of the argument above. So does this make sense to you?
It's a bit different, like, I mean, for like the rigid matrices or something, if you just make your matrix by using like the millionth through 2 millionth digits of pi, then
Yeah.
oh, it's gonna be rigid, right? I mean, why wouldn't it be?
Yeah.
On the other hand, like, that's something you just output yourself deterministically, so it's sort of not the sort of thing that works for avoid.
Yeah. So this is a very good point. It's like, actually I'm cheating here because there is a very important difference between range avoidance and all these construction problems, because all these problems are like uniform. You do not have any input. You are just given the impedance and you just want to construct something. All of them are uniform. And this range avoidance is actually non-uniform, where you are given the circuit and you want to analyze it. So this gives a very significant part of the hardness of avoid. And actually, in our paper, we will prove that under plausible assumption, range avoidance is hard. And this actually crucially relies on this observation. This is a very good point. Okay, let's jump to our results. Okay, so before going on to talk about our result, I want to like introduce another consequence of our paper. So, bounded arithmetic is something invented by Cook, which captures the complexity of reasoning. So it's like when you do computation, you consider complexity measured by the time you need with respect to the computation model. And because all these models we have simulate each other, you can say generally that it captures complexity of computation. And also we want to have this kind of things in logic, and actually Cook proposed a theory PV1, which stands for when you do proofs, you can only have the power of polynomial time in some sense, and what things you can prove. This is a theory PV1. So if you don't know it, you can imagine that it's very similar to piano, but all the induction you've done, the predicate in your induction can only be a polynomial time algorithm. In some sense, the PV1 is just this. You have piano, but all the algorithm, all the induction predicate you made must be polynomial time. So this theory is kind of mysterious because it cannot prove a one-way permutation is surjective. If you have a one-way permutation, then PV1 cannot prove the surjectiveness of the permutation. This is by some like witnessing results, which says that if you can prove surjectiveness, you must be able to invert it. On the other hand, it is strong enough to prove PCP0. So this, and also like most interesting result in circular bound, you can use PV1 or PV1 plus something to prove all of this. So it has quite a mysterious strength, because of course a permutation must be surjective, but it cannot prove it. But PCP theorem is supposed to be some hard things, and it can actually prove it. So there is an old question proposed by Krajek, who is also a very famous mathematician and logician, and he says whether PV1 can prove the dual-weak pigeonhole principle. So dual-weak pigeonhole principle is just what we have before. If n pigeons fly into two n holes, there must exist an anti-hole. So Krajek believes that this is true. This is false. PV1 cannot prove. But he said that he did not aware of any standard assumption that can imply this conjecture. And actually, after 20 years of he proposed this conjecture, we still don't find any reasonable standard assumption that implies this. And what makes this okay, so for example, if you have this dual-weak pigeonhole principle, you can prove in PV1 plus this principle that there exists a Boolean truth table that is hard based on your like natural version to prove it. So this is kind of a more fundamental, logical interpretation of the range avoidance reductions. So this is something like this. So what makes Krajek's question very appealing is that there is a argument made by a line of papers by Emil Hiraback, which states that PV1 plus the dual-weak pigeonhole principle is a right theory that characterizes probabilistic polynomial-time reasoning. So here the term probabilistic polynomial-time reasoning is kind of, it's not a formal definition, but he used some like results to argue that if you have the Dewey Pigeonhole principle, then you have most of the things you need in like complexity theory and cryptography for like probabilistic reasoning. For example, you get Chernoff bound, you get union bound, you get all this bound, and you can prove that any set defined by efficient circuit has a size. You can define the size of a set. So if you believe this, you will have all these probabilistic methods. So he argues that this is the right theory to capture probabilistic polynomial-time reasoning. So the question whether Dewey Pigeonhole principle is provable in PV is actually saying whether you can de-randomize probabilistic reasoning. So this is a apparently very interesting question, because if you can de-randomize the probabilistic reasoning, it reveals some fundamental strengths in proof complexity about probabilistic and deterministic reasoning. So does this make sense? Okay, cool. So here's the question. We have de-randomization of a range avoidance trivial algorithm. We have logic. And what I want to discuss today is that if we have witness encryption, we can resolve these two problems simultaneously. So this is our today's topic. So our first result is assuming NP is not equal to coNP and sub-exponentially secure witness encryption, we will prove that range avoidance cannot be solved in polynomial time. And the second theorem we have is assuming some stronger assumption of NP versus coNP style, which is NP cannot be infinitely often simulated. Oh, this should be coAM. I'm sorry, should be coAM. It's like coAM is like a randomized version of coNP, and this infinite often just means not only for infinitely many input lengths, but for almost all the input lengths, you cannot convert an NP algorithm to a coAM algorithm. So if you
What is AM?
AM is like asserting, so it's like a probabilistic version of NP where you have a prover and a verifier, and you can make constantly many interactions, and the prover wants to convince the verifier that the string is in the language. Okay. So it's asserting, and this should be co-AM. So assuming NP is not infinitely often in co-AM and sub-exponential secure witness encryption, we can prove that PV1 cannot prove the Pigeonhole principle. This kind of solves two very interesting problems using a similar approach. So because of time limitation, we will just prove the first theorem and leave the second theorem. But you are interested? Maybe you can say a word. It's like, although we say it's the logic result, actually our proof is not really about logic. So by some logic, knowing result in PV1, you can know that if PV1 can prove this principle, you will have an algorithm to solve range avoidance. But this algorithm is in polynomial time with constantly many queries to invert the circuit. So if you PV1 can prove this, you can automatically get an algorithm with inversion oracles, but only constantly many times to solve this range avoidance problem. So what we actually prove is that assuming these two assumptions, there is no algorithm even with constantly many inversion queries. So today we will only focus on the first, and I will try to give the full proof because it's quite simple. So are you ready for the second? Okay, cool. So before starting, we just define witness encryption in case you don't know that. Fixed and language LENP, for example, SAT, which is NP complete. And the encryption is given the security parameter and statement X. And you want to encrypt some message to ciphertext. And the decryption is you are given a security parameter, a statement, a ciphertext, and a witness to this statement, and you want to decrypt this message. So this means if the X is in this language, in case of SAT, it's like if the formula is satisfiable, then after you give an NP witness to this decryption algorithm, you can successfully decrypt the message.
Or B is a bit, what's the message, is it?
We can use a bit encryption or like string encryption because you can always like do them separately and use a hybrid argument to prove the correctness.
Okay.
So let's just imagine a bit encryption, but actually we will use a string encryption scheme, but essentially equivalent. So the security is that if the string is not in the language, for example, if the formula is unsatisfiable in case of that, then the encryption of 0 and 1 are indistinguishable. This encryption scheme is secure. So we will need the sub-exponential security, where it means there exists a constant epsilon greater than 0, such that this indistinguishability is 2 to the minus lambda to the epsilon indistinguishable against this size adversely. So lambda will be a security parameter that we can set, and this sub-exponential security just means it's sub-exponential with respect to the security parameter. And actually, this follows from the well-founded I/O by JLS, and this follows by some lattice-based construction and also in generic group models. So it should be a very plausible. Okay. So the idea of the proof is that if you have a deterministic algorithm for range avoidance, you not only got an algorithm, but also got a proof that the string you found must be also outside of the range of the circuit. So because it is deterministic and it is correct, you automatically got a certificate that the string you find is correct. So in such case, if we can like using this proof system to construct a better proof system for like onset, then you can solve coNP in NP. This is a very brief idea of our proof. So what we will prove is that if you have sub-exponentially secure witness encryption and you have deterministic algorithm for avoid, then you prove NP equals to coNP. And specifically, we will find a polynomial-time non-deterministic algorithm that check whether a string is unsatisfiable. Okay, here's the pen. We will just do the proof. So given the string phi, given the formula phi with an input, we fix the language to be set, which is in NP, where we are doing like witness encryption. And we output onset if and only if there exists a string y and there exists a random r, a string r, such that if we put this circuit into the range avoidance algorithm, it will output y. So this circuit is a decryption circuit of the witness encryption scheme, where the ciphertext is obtained by the encryption of y. So the thing is, after we non-deterministically search y and then r, we encrypt this string y over the statement phi with the randoms r and obtain a ciphertext. And then we construct this decryption circuit of this ciphertext, which is supposed to decrypt this ciphertext with a witness of the formula phi in case that it is satisfiable. So okay.
This construction is in NP or something?
Oh, this construction is in polynomial. So if you are given, so after you non-deterministically search y and the r, you can compute the ciphertext by yourself in polynomial time because this witness encryption is in polynomial time. And then you can construct this circuit. The circuit, after you get this circuit, you just fix the ciphertext in the decryption circuit of the witness encryption scheme. And this is also done by polynomial time. And then we run the range avoidance algorithm, which is also in polynomial time, and we can check whether the string obtained is y. So all these things below is in polynomial time. Right.
So is the non-deterministic searching the y and r like not in the reduction or?
So our algorithm to solve this unsatisfiability is you first search y and search r and then do things as follows.
Okay.
So this is a non-deterministic algorithm. You first search y, search r, and then you check whether after you encrypt it and put the decryption circuit inside, you obtain this y. So this is quite interesting construction where it's like you first encrypt your message and then use the avoid algorithm to find whether it is decryptable. So the intuition is that if phi is satisfiable, then this is decryptable. Then this is impossible because your algorithm should be correct. If we put the correct witness of this phi, this will be true. So there must exist. And in case that phi is unsatisfiable, your encryption should be secure. And no algorithm, including the avoid algorithm, should not be able to invert your secret Y, secret message. Okay.
So what prevents the avoid algorithm from finding, say, some different string Y star, Y prime? Right, because the avoid algorithm is only
Sure. Yeah, it is
some non-realizable.
Yeah, sure. So so this is only the intuition. So I will give the proof, phone proof in the next one. Okay.
Yeah, I'm a bit confused about the reduction.
Yeah.
Choosing Y and R non-deterministically.
Yeah.
But like, then you're trying to invoke the security of
Yeah.
speed, but if you choose R non-deterministically, it's not like a random string, right? There could exist.
Yeah,
R
sure.
that's like-
Yeah, it's quite interesting. Yeah.
Okay, so this is all gonna be taken.
Yes, it will be explained in the next one. So yeah, this is quite interesting because actually we are not like using it as a standard encryption scheme, but we will use the security thing in this proof in the analysis. Okay, so let's first prove the simple side, which is soundness, which means if the if the reduction tells you that it is a unsatisfiable string, then it must be unsatisfiable. So let's see. If the reduction says that phi is unsatisfiable, then it means there exists a Y and an R such that this is true. After you plug in all these things inside the circuit, the range avoidance algorithm successfully inverted. And then the correctness of the avoid algorithm will tell you that Y is not in the range of this circuit, which means that for any X, if you first encrypt it and you decrypt, you will not get Y. So what does it mean? It means that any string cannot make Y satisfied because otherwise, if you plug in this X inside, it should be able to correctly invert it because of the security of the witness encryption scheme. Because that our language is just satisfiability, if X satisfies Y, then the witness encryption should correctly decrypt, which means if you encrypt Y, you will get Y.
So this is the end, I guess I'm now confused about the because I guess in the definition of witness encryption, you're assuming that with probability 1 over the randomness, you can decrypt. So it's like with high probability, you can have then there'd be a bad randomness where the decryption actually fails.
So also here we assume the decryption is like perfectly correct.
Perfect.
Yeah. Here we assume that the decryption is perfectly correct. But actually, I think, you can also obtain something if you assume it's like with high probability, I guess. I'm sure it can. So if no strings can satisfy it, which means it's unsatisfiable. So the soundness is good. That is looks correct. So here we use the perfect correctness of this witness encryption scheme, and we use the correctness of the range avoidance algorithm. Make sense? Okay. So let's go to the hard part, which is completeness. Completeness just means if any string is unsatisfiable, our reduction will say unset. So let's say phi is an unsatisfiable formula. And let's look at the distribution where you encrypt an arbitrary string. In particular, you encrypt all1 string with a random R, where R is uniformly random. You can construct this, you can imagine this distribution. And this distribution, this avoid algorithm will give you a string of length n squared because it must somehow output a string, right? The circuit inside has input length with the input length of the circuit is n, and the output length is n squared because our circuit is like the where the circuit we constructed is like n squared length. We fixed it to be n squared length. So the decryption algorithm should also give a string of n squared length. So here, it must give you some string of n squared length. And in particular, there must be a string with length n squared, which is output by this avoid algorithm with probability larger than 2 to the minus n squared. Because there are only 2 to the n squared possibilities, there must be a string that is output with like larger than average probability. Is this true? Okay. So if phi is unsatisfiable, we will see that it does not matter whether you encrypt 1 or you encrypt this y star. So this is the security of the witness encryption. And in such case, if you consider the okay, so I think this should be y star. So if you consider the probability that you first encrypt y star and put the decryption circuit into the range avoidance algorithm, the accepted probability is differed by the probability here with only like additive factor of 2 to the minus lambda to the epsilon. So this means that it is this should be minus. Sorry. So the probability is 2 to the minus n squared minus 2 to the minus epsilon lambda to the epsilon. But if you choose this lambda to be sufficiently large polynomial in n, you will find this probability to be non-zero, to be positive. So there must be a string y star after you encrypt it and print the decryption circuit, put it inside the avoid algorithm. It will give back to the string you encrypted with positive probability. And this is what I mean by there must exist a random string such that if you give this, it will print out the string the message you originally want to propose. So the reduction will say offset. Does it make sense?
Where does the randomness come into play? Like so like what so for example, if R is just sample in a domain that has only one element.
Oh yeah, sure. So this is the thing. So witness encryption, if you look back to the definition of witness encryption, it says that you can arbitrarily choose a security parameter and it will ensure the security on that side. So to make that to be true, you must have the randomness to be a polynomial related to your security parameter, because otherwise you cannot get the security. So this means that so the thing is you can first choose the lambda to be sufficiently large, and then it will automatically generate a random string that is long enough to make this to happen. Does this make sense? Sounds good. Sounds good. Okay. So so now we prove now you can see that the reduction is just to find a string y, to find a string r, and encrypt it, put the decryption circuit, and see whether okay.
Is there a reason why you put n squared as the length?
It doesn't actually matter. So it's like you can put it as long as you put it to be longer than n, which is the impotence. Okay. You can make it to be done. And the thing is you can put an arbitrary polynomial here, which because if your stretch is larger, the problem is tend to be easier. So even if you fix the large to be quite large, we can still prove the hardness. This is the thing. So actually this reduction is quite simple, and you can like adapt it to tune the parameters to prove some like finer result, which says that avoid is not only hard against polynomial, but also hard against stronger thing if you assume stronger assumptions. So this is also done in the paper, but it's conceptually just this result. Okay, so this is takeaway. So all the explicit construction reduced to avoid. For example, circular boundary matrices, Ramsey graph extractors, code, and everything reduces to avoid.
Have you finished like the entire like reduction algorithm?
Yeah. Oh,
How do you how do you deal with this non-deterministic choosing Y and R?
Because you are a non-deterministic algorithm, right? What we are proving is that unsatisfiability can be solved by non-deterministic algorithm. So we have the non-deterministic power.
So you're proving unset is in NP.
Yes, correct. So you can see this. This is our plan. So we want to prove NP equals coNP, which is like unset can be solved in.
Okay, so just to clarify, so unset is coNP complete.
Yes.
Okay.
Yes. Cool. So if you want to remember something, all explicit construction is reduced to avoid, at least most of them. And avoid cannot be solved in polynomial time because of witness encryption and NP not equal to coNP, unless you have luck, you have some luck, or you have some magic, which means randomness or NP algorithm. So thanks for listening. This is all my presentation today. So any questions?
Is it widely believed that NP is not coNP?
Yes, it is. Actually, we believe polynomial time hierarchy does not collapse, which means that like P to the NP to the NP to the NP does not NP to the NP to the NP to the NP is different from coNP to the NP to the NP. Something like this for arbitrarily large level. We do believe like the polynomial time hierarchy doesn't collapse. And I think people believe more on this assumption than witness encryption, I suppose. I don't think no one would disagree. So yeah.
So like a reasonably simple candidate for witness encryption, or not that simple?
It relies on indistinguishability obfuscation for the most part.
There's a
Yeah, we have a page on this.
I'm just wondering, are they like very complicated or like not that complicated?
I think the existing like system are quite complicated.
I think.
Yeah, we have a page on this.
Going too far.
Oh,
Back.
oh, I forgot. Sorry. Yeah, go too far. Yeah, here's the page. So yeah, so we can use well-founded IO, and actually in our paper we just use IO as assumption because people quite like this result. And what we did is just implement the witness encryption scheme using IO. And you also have some other construction which is like lattice-based, but they are not quite different from like the standard lattice crypto system. They use some strange assumptions, or they don't. I think in the first paper they don't even prove the security. They just propose a system and claim it's kind of secure. And later on, people have some analysis which use some non-standard assumption to prove the security. And also, if you have generic group model, you can construct witness encryption, but generic group, you need some instantiation.
I see. So the other two boxes are somewhat non-standard.
Non-standard, but it doesn't mean that they are like less plausible, because witness encryption also relies on some heavy result. It's just like we have some like well-founded. So it's kind of, yeah, I think, I'm not sure whether you guys believe, but it's like witness encryption is still like quite weaker, much weaker than IO. I'm not sure whether you agree, but it's a weaker system than IO.
Just IO for null circuits.
Yeah, for sure. It's a very special case of IO.
Oh, so this generic group model construction, it also depends on another.
Yeah, sure.
Like
It depends on
NP hardness of this.
Yeah, they assume a very efficient city.
Yeah.
Or you assume a very strong hardness of approximation.
Yeah.